class it is. Finally look at screens. So in about a week, I'm coming in with pink glasses.
So rose-colored glasses lets you see the screen better?
It stops with the light and they stop the reflection with light, or they help with migraine.
Oh, okay.
They're
Oh, migraine stuff. Okay, got you.
They're rose colored, so the lenses will be a pinkish tint, and I'm getting new frames.
Nice.
So they're usually colored pet. So I'm not wearing sunglasses.
All right, I'm recording class. Ask me, anyone have any issues with the homework over the weekend? Number. All right. So clearly you missed Friday's class, so let's see if you can at least, because we'll do a little bit like what was on Friday as well too. Okay. All right, so we're still in the transformation mode. We did sine cosine, so that would lead you to believe
We're doing
tangent, cotangent, secant, cosecant. We're gonna do all four in one day, right? All four in one day. And the reason why you can do all four in one day is because the process doesn't really change. The only thing we truly need are those mini table of panes, or for the parent function of those functions to graph.
Oh,
Quiz on next Friday. Right? Is that what it said? Yeah, next Friday. That's our next big why don't we have school? I'm okay.
Oh. Why do we have Veterans Day off? Or we don't have Veterans Day off, or we have it?
I'm with you. I'm with you. I don't know.
My mom gets it off.
I'll just say the basic philosophy of the school was every month we'll have at least one holiday. And so since May, we already get that, you know, we end before the end of the year. I think that's what they were thinking. I don't know.
I thought Veterans Day was in November.
Well, we get Thanksgiving in November.
Yeah, but don't we still get it on a day off?
No, we don't. No, I that's exactly why. I'm just saying I don't agree with it. I would like to have Veterans Day off. We can get it off. All right. So here we go. Homework tonight. Once again, this is quickly done as long as you have that parent function table pane. By now you've done transformation so much it's pretty quickly done. If you have the parent function in front of your face, you should be able to do each problem in less than a minute. It should be that easy. In fact, I'll try to prove to you how quickly it can be done with the first example. Yep. Well, I'm going to give you some notes about tangent, cotangent, secant, cosecant, but yeah, and then I'm just going to hand you the parent function and away you go. All right. So yes, it's the graph of the last four that we haven't done. All right. So seems like a lot to do in one day, but once again, we already have a process. If you have the parent function table, then all you're doing is applying those transformations to those values and you're graphing. Okay. These are the weird ones. All of these will have vertical asymptotes. So this one takes a little bit more kind of discussion because we have vertical asymptotes involved. Okay. So we have the parent function for each. We apply the transformations to it and we're done. We just graph that. All right. Well, last few classes we did sine, cosine. Do a quick review, right? So for sine and cosine, remember the period is 2 pi for each, right? We have a formula for period now. It's 2 pi divided by omega, right? And then it turns out that when we get to the next two, which are tangent, cotangent, we'll save secant, cosecant for the very end. We do tangent, cotangent. The period is no longer 2 pi. I don't know if you remember this, but we did graph tangent and cotangent on our calculators. And what we saw for tangent, cotangent, that one cycle of it is pi. Like it only takes 180 degrees to get to the complete picture of it. For sine, it takes a full 360 degrees or 2 pi to make one full cycle. But for tangent, cotangent, it only takes 180 degrees or pi to get to one complete cycle. All right. So the only thing we would have to do if we wanted to have a formula for a period, notice this is in a box. We don't need to write this down. The only thing we'd have to do here is get rid of the 2 and the formula would still work. Right? Okay, so let's talk about tangent first. So for tangent, remember, tangent is defined as y over x on the unit circle. Anybody see a problem with this? Anybody see a problem with this? I'll point to it. Anybody see a problem with it?
X can't be 0.
X can't be 0, and guess what? X can be 0 on the unit circle. Where is x equal to 0 on the unit circle? No, x is actually 1 right there.
It's pi over 2
90 degrees
and 3
and negative 90 degrees or 270 degrees. In terms of radians, that's pi over 2 and 3 pi over 2. So we will, in fact, get to, well, if it's 0, then what's going to happen when I try to graph? It's undefined. So we're going to get two values where it's undefined. And so notice I'm not going from x values. I'm not going from x value 0 to 2 pi. Remember we said tangent only goes 180 degrees. If I went from 0 to 180 degrees, right, then these undefined values would kind of be squeezed in between. We just say it would kind of make more sense if we do our parent function if we have it squeezed between the two undefined values. So for sine and cosine, we go from 0 to 2 pi. For tangent, cotangent, we're going to do only 180 degrees, but we're going to choose those positions. And it just makes sense to squeeze it between the two vertical asymptotes. And the vertical asymptotes for tangent occur at negative 90 and positive 90, or negative pi over 2 and pi over 2, or 3 pi over 2 and pi over 2. Does that make sense? Okay. That's an ugly table of pain. What would make more sense?
If we simplify it to new one,
So which ones you want?
undefined 0,
We want the undefined because that's what's literally going to bookend the function.
negative
Hey, how about we pick the nice friendly ones? Negative 1, 0, and 1. And those are the ones we're going to pick. Okay, so that's going to be our thing. And look, there's a one cycle of the tangent function. Notice it's squeezed on the left. I didn't draw the vertical asymptote, but at negative pi over 2, then it comes up, goes through 0, 0, goes all the way up to positive infinity. We get another vertical asymptote of pi over 2. So that's going to be our bookends, negative pi over 2 and pi over 2. Hey, here's a whole bunch of them put together. Notice we get vertical asymptotes, vertical asymptotes, vertical asymptotes, all over the place. Okay. All right, so we're going to write down, remember we wrote down notes on sine and cosine. We're going to do the same thing for the four function. This is the hardest part of the class, is writing this stuff down. Hey, you see on box number 2, it's got a heading. Just scratch that heading. I don't know why I put that there. Okay, so notes, I'm going to show them all to you. I'll talk through them quickly. You just need to copy them down. Hey, sine and cosine, you never need to lift your pencil up when you draw the sine and cosine because they're continuous. But tangent is not a continuous function. You have lots and lots and lots of vertical asymptotes here. So it is not a continuous function, right? The domain, remember those are the allowable x values. Well, we'll have to exclude all those vertical asymptotes. The vertical asymptotes occur at odd values of pi over 2. 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, or in the negative direction, negative 1, negative 3, negative 5 pi over 2. But every other x value is allowed. So basically, it's all the reals excluding odd values of pi over 2. Does that make sense? Third one, hey, it goes from negative infinity to positive infinity for the range. The y values are every single, all real numbers. The previous class said, why didn't you just write all real numbers? And I said, yeah, why didn't I write all real numbers? I guess that would be an easier way of writing it. Remember, OEO, it is an odd function. Sine, cosine, tangent, cosecant, secant, cotangent, OEO, odd, even, odd. Now you remember it. If it's an odd function, that means if you do the negative of the angle, so tangent of negative theta, you can take the negative, throw it out front because it's an odd function. It doesn't have a period of 2 pi. One complete cycle is done in pi. 180 degrees. But notice we're gonna use from negative pi over 2 to positive pi over 2. That's 180 degrees. From negative 90 to positive 90 is 180 degrees. You get lots and lots and lots of x-intercepts. If the vertical tangents happen at odd powers of pi over 2, then the x-intercepts are going to happen at even powers. Well, if they're even, then that would be 2 pi over 2, which is pi, 4 pi over 2, which would be 2 pi, so forth and so on. So whether you want to write it as the x-intercepts are even values of pi over 2, or just simply write pi or 0, pi, 2 pi, 4 pi, 6 pi, and the same thing in the negative direction, that's fine. It has one y-intercept, and that's at 0. So it does go through the y-axis one time at 0. And then the last one, where the vertical asymptotes, well, they happen where the domain is undefined. So odd powers of pi over 2, negative 1, 1, 3, 5, so forth and so on. And then I'll stop talking and allow you to copy these down. Yes. A Band-Aid? Absolutely. These are Madison's. She put it in. There's 2. Don't say I never gave you anything.
This year, I'm having an academic comeback. Okay, I had a C,
We gotta be a B. We want a B or an A.
B plus.
Yeah. All right, that's between a B and an
If I don't get a B plus, guys, I will not walk in this class. I will not walk that stage.
A. It's a bold statement.
Put it on.
What does that mean about its dodgeball mean?
If you can dodge a wrench, you can dodge a ball.
No, the other one.
Oh,
Whenever someone
That's
says
why.
whenever somebody says a bold statement, they always say, oh, that's a bold move, and there's a name. I forget what the name is. It's from the movie Dodgeball. That's a bold move, blah, 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 whatever he says. Cotton, I think it is. I'll have to look that one up. All right. All right, everybody good? Leave? Okay. All right. So this will be quick because we already know how to graph functions. We just got to follow that cut down table of values, which we didn't write down. So we'll do cotangent before we do a graph of one of them, because they're just table of values, right? We're going to apply the same thing. So cotangent is going to have a problem when. So where is y equals 0? Agreed. So where is y equal to 0? On the unit circle, y is never 0.
Y is equal to 0 and 0.
And.
Is that wrong?
And
Is that wrong?
one other, you keep. Okay, it's 0 at 2 pi, 4 pi, 6 pi. There's one other spot where y is equal to 0.
It's 0 in the middle.
So we,
0, 0.
yeah, but that's not on the unit circle. At pi, right? So at 0 and pi, the two angle measurements, that's where the y value is 0. So therefore, we're going to get. This is the table of values for tangent. Remember, it went from negative pi over 2 to pi over 2, but perfectly fine for cotangent. So if we want to bookend it between undefined values, we want to go from what two things give us problem?
Pi and 2 pi.
That's the same value. Oh, no, sorry, you said it right. I wasn't listening to you. Yes, let's go between 0 and pi. She said 0 or pi and 2 pi. I'm going to go with 0 and pi. That's the same as 2 pi. 0 is the same as 2 pi. Okay, so now we have a bookmark between the two undefined or the vertical asymptotes. Okay, yay for us. All right, so the difference between tangent cotangent is, well, I'm saying the difference between the two are, I don't have them next to each
That
other.
it doesn't touch.
Okay, so 0 degrees is right here. We're going to get a vertical asymptote right there. It's been shifted over. You see?
pi.
Pi over 2, remember tangent went through 0, 0. This one doesn't, so it's been shifted over pi over 2, and its basic shape is, as compared to tangent,
Flipped over the.
it's not over the y because the y is way over here, but it looks like it's been flipped horizontally, right? That makes sense? Okay, so there's a whole bunch of them together. Once again, for tangent, it went through 0, 0, but on cotangent, we get a vertical asymptote right there. So same basic notes for, and this is box 2, same basic notes for cotangent, I'll throw them all up. It's the same basic statements, right? It's still not continuous. It still has vertical asymptotes. The vertical asymptotes are multiples of pi. So everywhere you got a pi, 1 pi, 2 pi, 3 pi, 4 pi, we get vertical asymptotes. Remember, for tangent, it was for odd multiples of pi over 2. For cotangent, it's all the multipliers of pi. Negative 3 pi, negative 2 pi, negative 1 pi, 0, 1 pi, 2 pi, 3 pi, 4 pi. We still get all real numbers for the range. O, E, O, so it's still odd. Has a period of pi, or 180 degrees. So the x-intercepts don't happen at pi's now. It's kind of like the opposite of tangent. So tangent happens in terms of pi's. This one happens in pi's over 2. And once again, odd. X-intercepts are the odd pi's over 2. Even pi's over 2 would be where the vertical asymptotes occur. Finally, the vertical asymptotes are multiples of pi, just like what we excluded for our domain. If you're starting to do your homework, wait for secant, cosecant. You can do your tangent, cotangent ones. You can do them out of order, I don't care. But I'm going to give you the easy way to do secant, cosecant. The glasses you're gonna get, so. Oh, nice. Did I ever tell you my oldest daughter contact story? Boy, there were tears. Boy, there were tears. I remember, like, she was so excited. I was excited. My wife was excited, and they got home and they were going to put it in the first time. And it was like, all of a sudden there was mom, daughter, like, put your daughter contacts in. And then it was crying. And I was like, I'm going for a walk with the dog. Okay, touching your eyeball is not a natural thing, right? Right. But I'll just say for some people, that's not a natural thing. So hopefully you don't have the same thing. But she was probably, I don't know, it was in high school when she did. I don't remember what year it was, but I remember that one being like, I'm taking the dog for a walk. When I came home, it was all fixed and stuff.
Everybody's like.
No police were called, so it was apparently worked out,
Have just an appointment to teach you how to put the contacts.
That's what I said. I was like, they came home from the store. I was like, didn't you already do this?
Did you see that? Okay.
That's how she sneezes.
Well, like, it sounds like a chipmunk getting stepped on. Yeah.
You step on a chipmunk?
No, but like.
How would you know what that sounded like then? Yes?
I think it was Theodore, and he makes a noise just
Oh,
like
okay.
that.
All right, that makes sense.
And I'm just-
All right, do we have everything copied down? All right, moving on. So the actual graphing part is kind of like the slow and easy part. Who thinks they have the worst grasp of this material right now? Priscilla? Well, you did Miss Friday, right? Remember, this is still into effect. This is the part you missed, Priscilla, right? Is we still have the alpha, we have the omega, we also have beta. Alpha and omega influence what? The y's, and the omega is the x. And remember, the x is going to be the opposite. If it's multiply, you divide, right? If it's dividing, you multiply. Okay, so the alpha is your vertical stretch or compression. Your omega is your horizontal stretch or compression, and your beta is your vertical shift up or down. Okay, I shouldn't have to write that down. It's the same thing we've done. So we're going to be not lazy, we're going to be efficient, and we're going to pick values for tangent, cotangent that make our life easy. I don't want to use all that stuff. We all agreed that the easiest way would be pick the nice friendly ones, write this one down. These are the values to use for tangent to make your life easy. So it's not that we're making our graph inaccurate because we're skipping some stuff. It's just that, well, we know that the general shape of tangent, cotangent, we're going to pick 4 evenly, technically 5 evenly spaced values, and we're going to pick the values that are squeezed between the 2 vertical asymptotes. For tangent, the vertical asymptotes happen at -90 and +90, or negative pi over 2 and pi over 2. And then we don't have to worry about the square root of 3 or square root of 3 over 3. So our graph, if you freehand it, will be slightly inaccurate because you're probably not going through exactly the right values, but you have the basic general shape. If we want to be really accurate, then we probably should be using our calculators. But if we're asked to graph this by hand, we can get a graph that's pretty darn close to the exact thing, at least close enough so that if we have questions on its general shape, we can answer those questions. All right, everybody's got it copied down? So that's tangent, right? Remember, we had 2 methods for graphing. Method number 1 was we use that table, right? And we modify it by the transformations. Method number 2 is we use alpha and omega. We use those 2 formulas. Amplitude is the absolute value of A. Omega, in our case, since the period of this would be pi, T would be equal to pi over omega. Of the 2, which one do you like the best? She likes 2? Yeah. Most people would probably say method number 1,
2.
right? But 2 is fine as long as you understand the values that you want for your table. So I'm going to show you method number 1. And if you like method number 2, then we can do some of those as well too. All right. So here's our first example. Step number 1 is don't screw it up. Make sure you understand which trig function we're using. Which trig function are we using? We're using tangent. Now, eventually we're going to have all 6, so we're going to have 6 values to consider. So make sure that you pick the right one. So we're using tangent. We decided to use method number 1. So method number 1 uses this table of values right here. Okay? All right. Priscilla, you still think you have the weakest grasp of this? Seth? Who thinks they have the weakest grasp of this? All right. So Matt, it's you then, since nobody wants to volunteer. All right, Matt, I see a bunch of values up here. I see a table that we have to modify. What are you thinking? Okay. Okay, so which one are you going to do first? The ones that affect the X or the ones that affect the Y? Doesn't make a difference. Thank you for choosing Y. Only because it will match my, if you want to do X first, perfectly fine. But my slideshow is using the Y's first. It's not because it's smarter, it's just the way I did it. Okay, so which values up here affect the Y? The outside. What's on the outside? A 2 and a -1. Both of those affect the Y values. You just need to remember which one you do first. You do the 2 first or the -1 first. We do the inside first, or the one closest to the X, and that would be the 2. Then we do the -1. So you're always going to do your multiplication, division, and then you're adding and subtracting. Okay, so take all your Y values and, well, tell me what to do. But the first one is undefined, so what do? We just keep it undefined, right? So the Y values, right, if you're multiplying by 2 and it's undefined, it's still going to say undefined. How about the other values? So he multiplied those, he's going to do it in 2 steps. So we multiply all these by 2, so -2, 0, 2, undefined, and then subtract 1. So that's going to turn into eventually -3, -1, and 1. Okay, so we take those two values. Mr. Chartier. Oh yeah, I'm not sure if she's. I have physically not seen her. She was told that she was going to be either a TA to somebody, or maybe an office aide, but she is. I physically have not seen her. Presley niece. Yep. I have not seen her, so I mean, I couldn't say that she's here or not. But last week we had the conversation for this semester. She only had me for one semester for a math class. That was last semester, and then this one, at least the conversation I had with her was that she was going to be a TA for a class or an office assistant. So, okay, okay, we'll do. All right, bye. Thank you. Okay, sorry for the delay.
Make it look like a,
It would just flip it, right? All the y values. Well, I'm saying we flip it like this.
so it would look like a 13.
It would, wouldn't it? Right. Okay. We're on Matt. What are we going to do for the x values? He says nothing. Why? What's omega? Technically, it's 1, and 1 wouldn't change anything. We're multiplying. So omega in this case doesn't exist, or it's 1, and what doesn't change anything. Yay! I got my table. Now what? Okay, how am I going to graph it? Okay. How many are we going to make? Or are you talking about x's or y's?
On the x's.
Now look at the x values and tell me something smart. I'll agree we're going to make 4 tick marks on the x-axis, but where are those tick marks going to go? How many on each side? She says, looking at and you got to do it individually for each one because it could change. Looking at these values, we got 2 negatives and 2 positives and a 0. So 2 on the left, 2 on the right, and I did the y values first. Sorry. I don't know why I'm doing the y values first. Okay, but you were correct for the x, and how about for the y's? And what will they be?
-3, -1.
Yeah, but if you got to do -3 and -1, then you probably should.
Say -1, -1, and -3.
I'd do a -2 as well. Because how would you evenly space it? Agreed, but I'm saying just to make it look neater, we probably would put that -2. So I'm going to say I'm going to go -1, -2, -3, and then a +1. Just try to do that. And then you were right on the x or the y value, x value. Sorry. Okay, cool. Once that's done, if you want to press me, label, right? If you don't label, I would at least label the highest and lowest of both the x's and the y's so that you leave no doubt to the reader. And then we put dots where they need to go. Oh, vertical asymptotes where they need to go. I put my dots, and what's the basic shape of tangent? So we're starting close to the left asymptote. We go up to the first dot. We're not making a straight line. We're making a curve. That's a horrible curve, and that's the worst one I have today. My other ones look pretty good, but that one doesn't look good at all. But that's the shape. Does that make sense? It's just like the last 2 days. It's not bad at all. So that's tangents. We should probably do everybody good on this one? So we should probably do a cotangent one, except we didn't do omega, so let's do one with an omega this time. All right, I'll do this one really quickly. Okay, ready? First thing I do is identify the function. The function is tangent. So I pull up my tangent parent function, okay, or parent table. Hey, I have nothing affecting the y's. Do you see that? There's nothing in front, nothing on the other end, so y's stay the same. Pi over 2 is omega. What do we do with omega? we take, we can do that, right? We can also, if we use technique number one, is we multiply everything by whatever that is, except we do the opposite. So instead of multiplying by pi over 2, we're going to divide by pi over 2. So the first one is negative pi over 2. That's my first x value. And we're supposed to divide by, which would cause it to flip. So it would be times 2 over pi. And notice what happens. And you're left with 1, negative 1. So that would give us a negative 1. Are you okay if I do the rest of them for you?
Yes.
Okay. So all I'm doing is multiplying by 2 over pi. Each time, by the way, the pi's would cancel on each one. So if the pi would cancel, you get negative 2 over 4, which is negative a half. Well, 0 is still going to be 0. And once again, it would be 2 over 4, which would be a half for the other one. There you go. And then the process is the same to graph. All right, somebody tell me how to graph this. You talking about y's or x's?
Why?
Okay, so the highest would be 1, the lowest would be.
Negative 1.
So how many tick marks do I need? If you want to count the middle as 1, right?
Yeah.
So just 1 above, 1 below. So there's your y's. How about for your x's?
You would just need, one, and then you need a 1 for 0.5, 1 for negative.
So how many tick marks left and right? So how many tick marks left
5,
and how many tick marks right?
2 and 2.
2 and 2. 5 would count the middle, right?
Yeah.
So 2 left and right and 1 up and down. Make sense? Label, 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 label. Vertical asymptotes on the ends. And then tick mark, tick mark, tick mark. And then the basic shape. Well, if you have those 3 tick marks or 3 points in the middle, you know the basic shape. Hey, that one is actually what it looks like. I don't know why I can't make the previous one look right, but that one's the way it looks like. Okay, so there's your tangent. Yes? All right. So cotangent, once again, we still have 2 vertical asymptotes that squeeze it. We're just going to get rid of all the square roots of 3's and the square roots of 3's over 3, and we're left with, write this one down. There's your cotangent. Cotangent doesn't go from negative pi over 2 to pi over 2. It goes from 0 to pi. It's still squeezed by those vertical asymptotes. You still have 1's and negative 1's, but those are also flipped around. Remember, for tangent, it started at negative 1 and then to positive 1. This one starts at 1 and goes to negative 1. And that's a result of it being flipped around. We're okay? All right. So Leaf, you're gonna have to get caught up. We're gonna do a cotangent one. Here's the parent table. All right, so here we go. Cotangent. We start off with the parent table. And what's happening here? All the y's by 3, so that would give me. Well, that was easy. So all the y's by 3, and then for all the x values, we're going to divide by 2, so that would be 0. Dividing by 2 is the same as multiplying by a half. So multiply pi over 4 times a half. Visualize it. Pi over 4 times a half. Can't visualize it, I'm going to draw it. Which would be. You were so close. You said it right. You said take pi over 4 and multiply it by 1/2. Then just multiply straight across. Pi over 8. And then that would be pi over 4. This would be 3 pi over 8. So there's where our values are. Why is this not clicking? Oh, there we go. All right, cool. Leaf, you got the parent one for cotangent? Okay. All right, somebody tell me something smart. How are we going to do this one? My God, it's just completely done. I just need to graph this. So I need tick marks. He's saying for y's, we're just going to use 1 tick mark because it's 3 and -3. Could I put 3 tick marks above, 3 tick marks below? I could, right? And the reason why we did that on the first one, because it was -3 and -1, it just made sense to put a -2 there. In this case, we're just going from -3 to positive. So yeah, I'm going to agree with him. 1 tick mark above, 1 tick mark below. All right, how about left and right? What are we doing? Look at the values. Four tick marks all on the right. We don't have any negative values, so we don't need anything negative. There we go. 1 above, 1 below. Starts with a vertical asymptote at 0. And then dot, dot, dot. It's not a straight line because we have another vertical asymptote. It's going to have a curve. So in this particular one, it curves from upper left to lower right. And there we go. Yes? Okay. Not too bad. What do we got left? Secant and cosecant, right? So there's 2 left to go. Secant and cosecant are kind of special, right? Reminder, remember how we actually, because sometimes you just want to put your graph calculator to check your work, right? Do you remember how we graphed cosecant and secant? 1 over blah, blah, blah. Yes. What's the blah, 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 though?
It's opposite. Or it's inverse. Yeah, that's that way.
Yeah, but you don't have a cosecant button on your calculator. You're close. You kind of remember what we did. How did we graph cosecant? Anybody?
Cosecant is 1 over
It's
1
equal.
over or
So close.
1 over sine.
It's 1 over sine. Remember, cosecant is 1 over sine. Secant is 1 over cosine. So if you wanted to graph this, you'd have to, if you want to graph cosecant, you'd have to graph 1 over sine. That is the same function. Okay.
Thinking out loud here.
So she's trying to think out loud like where this is going. I'm actually going to give you an entirely new way of doing this that's easy, right? So also note, right, that if you graph both of these together, everybody's got their calculator, grab it out. Do you remember doing this? We graph both of them together. First function is, and the second one is cosecant. Now remember, that's cosecant in disguise. So I want you to graph both of these. Now remember, you don't have, unless you're Seth, he has cosecant button on his calculator. I want you to graph sine and 1 over sine all on one graph. And just see the basic shape. And this will reveal the way that we're going to graph this. And remember, if your zoom is off, then you're going to hit zoom trig for it to look nice. And if you did it correctly, you should get that picture right there, where red is sine and black is cosecant, right? All right, now if we look at this, notice for the black portion, if we want to graph one cycle of it, you got a smiley face and a frowny face, make one cycle, the black part. And then it just keeps repeating itself over and over again. Unfortunately, I didn't put a vertical asymptote at 0, 0, but there's a vertical asymptote at 0, 0. Notice we have, just like tangent, cotangent, we have lots of vertical asymptotes. So there's your sine and your cosecant together, right? The same thing will occur if we did this with cosine and secant, right? Except it's going to be shifted over 90 degrees. Notice this one doesn't go through 0, 0. Well, none of them do, secant or cosecant. But this one has a vertical asymptote at 0, 0. If we did the same thing for cosine, and that's not 1 over cosine, that's actually secant, right? If we did the same thing, we'd get this. And now notice, now here's 0, right? That the smiley face of the black right here is right over with 0. Okay? So that's the basic shape. Ignore the red for both of them. Notice if you squint your eyes, you can't tell any difference between secant and cosecant. The black portion looks exactly the same. Smiley face, frowny face, smiley face, frowny face. The same thing. The only difference, it's been shifted 90 degrees, left or right. Does that make sense? All right, keep that picture in the back of your mind. We're going to do the notes on both first, and then we'll get to the graph part, okay? All right, so here's all the notes on cosecant. It's not continuous. It's got vertical asymptotes. So the domain is all real numbers excluding those vertical asymptotes. And for cosecant, those vertical asymptotes happen at multiples of pi. So 0, pi, 1 pi, 2 pi, 3 pi, 4 pi, so forth. Which would mean last statement, and the vertical asymptotes happen at those multiples of pi. The range, that black portion doesn't touch any value between -1 and +1, excluding -1 and +1. So we say that the range is from -1 to -infinity and 1 to infinity. I said that backwards, but same idea. OEO. Cosecant goes with sine, so therefore it's an odd function. Its period, unlike cotangent, tangent, which is pi, its period is the same as sine, which is 2 pi. There are no intercepts at all for cosecant. It doesn't touch the x, and it definitely doesn't touch the y. At y equals 0 and x equals 0, there's a vertical asymptote because that's a multiple of pi. And those are all the notes on cosecant. It's 2 pi. 2 pi.
It's just.
Oh, t equals 2 pi over omega. Same thing.
Yeah.
Yeah. But the same thing as in previous nights. Like tonight, when you graph it by hand, I don't need 26 periods. I just need 1 period. Just draw it one time. And for cosecant, it's going to be between 0 and 2 pi. Now, Abby, I'm going to show you a different way of graphing it. It's very easy. The only difference between cosecant and the next one we write down is secants for these statements. Everything's the same except where the vertical asymptotes occur. It's going to have the same range. It's not going to be an odd function. It's going to be an even function. Okay. So here are all the notes on secant. It's still not continuous. Okay. But you're going to have vertical asymptotes at pi over 2 and all odd values of that. Therefore, the domain includes everything except where those vertical asymptotes are at. Has exactly the same range. 1 to pi and -1 to -pi. Even function still has a period of 2. Since this one does go through 0, 0, right? It does have a y-intercept. I'm sorry, it doesn't go through 0, 0, it goes through 0, 1. Sorry. And those vertical asymptotes happen at odd multiples of pi over 2. 1 pi over 2, 3 pi over 2, 5 pi over 2, and they're negative partners. -1, -3, -5, pi over 2. You know, I've debated whether or not that would be more efficient or more confusing. And so my thought behind it is, let me get to where they're not even worrying about the transformations. Like you guys can do that almost in your heads now. I think that's more efficient than let's do sine and then let's do cosecant and then let's do cosine and then cosecant. But that is an option. Very good. Okay, so I promised you a different method of graphing secant, cosecant, or cosecant, secant. All right, so let's see who's got the biggest brain. All right. Do you see what I've done?
Yeah.
I got cosecant on the left. I have secant on the right. On both times, I graph sine and cosine along with it because look what happens. Like, let's look at cosecant over here. Notice red is your sine. Where the x-intercepts or sine are at are where the vertical asymptotes occur. Where the high and the low points of sine are where cosecant starts. Cosecant starts at the high point of sine and the low point of sine. I guess what I'm saying is if you graph sine, which we already know how to do, and we have a cut down table for sine, then you can turn sine into cosecant really easy. So the technique I'm going to say is if you have cosecant graph sine, put vertical asymptotes where the x-intercepts are at, put a dot at the mins and the max, and then draw a smiley face, frowny face, and you're done. That's going to be the technique. So the mins and max of cosecant or sine and cosine are where cosecant and secant start. And then the x-intercepts of sine or cosine are where the vertical asymptotes or cosecant and secant are. It'll make more sense when we do one example. Okay, you follow the basic logic? So let's see how that works. Okay, there are steps. It looks complicated. It ain't that bad. So here's the thing. What's the function I'm doing? So instead of graphing cosecant, I'm going to graph sine. So I'm going to do the same function, but I'm going to graph the sine function. So I'm graphing the same one. I'm going to exclude the -1 because it's not important to find the x-intercepts, right? And mins and max. Okay. All right, cool. So let's do that. Remember the cut down table for sine? Sine went from 0 to 2 pi, and then went 0, 1, 0, -1, back to 0. So there's your cut down table for sine. 0, 1, 0, -1, 0. Hey, what's happening to the y values? They're multiplying by 2. So I take all the y values of sine, multiplied by -2. Anything happening to omega? So it goes 0, pi over 2, pi, 3 pi over 2, 2 pi. The normal table. So the technique is I'm going to graph sine. All right. Oh, I need 2 tick marks. Okay, so there's my sine. Right? Yes? Everywhere there's an x-intercept, I should draw vertical asymptote. So everywhere on my sine function that I have an x-intercept, I'm going to draw vertical asymptotes. I agree. I used yellow. I should have used a different color if I used yellow. You see what I did? Everywhere there's an x-intercept, I draw vertical asymptotes. And then I'm done with vertical asymptotes. That's where they're at. Now I simply need to do is find the mins and the maxes. Right? We know for sine function, the max is always, right? In this case, it's 2. Except we didn't do anything with this -1. What do we got to do? Subtract 1. So we subtract 1, which would put the max now at 1, and we draw a smiley face. And do the same thing for frowny face. There's a min that occurs here, except we have to subtract 1. So we subtract 1, this -2 turns into, and then draw a frowny face. And then we're done. Because remember, smiley faces and frowny faces occur at mins and max of the sine function. The only thing I have to do is now take these blue and shift them down 1 shift. See what I did? I'm just shifting all those down 1 and I'm done. So instead of having 6 tables of values to remember, you only need 4. You need sine, cosine, cotangent, and tangent. And that's it to use technique number 1. So I'll back this up one more time. Okay, we're going to graph sine. So I graph sine. I come up with this table of pain for sine. I graph very lightly. You can do it with dashed lines or just very light with your pencil. I graph sine. Everywhere there's an x-intercept, now I'm going to put vertical asymptotes. And then wherever there's a max, I'm gonna subtract 1 and put a dot, draw a smiley face. Wherever there's a min, I'm gonna subtract 1 and draw a frowny face, using my vertical asymptotes as your bookends or your guides. Right? So there's my, before I subtracted 1, and then I move them down 1 for my final answer. Yay. Does that make sense? So if this had been secant instead of cosecant, we would have done this for cosine. But the rest would be the same. Wherever cosine has an x-intercept, those become vertical asymptotes. And wherever the max is for cosine, we put a dot, draw a smiley face. Wherever there's a min, I put a dot, draw a frowny face. And that's it. That's how you do cosecant and secant. Now, if that doesn't float your boat, you're like, no, I want to cut down table of values. Then you go to your unit circle. We pick the same basic values for sine and cosine, or for secant, cosecant, right? Here's cosecant, right? Cosecant goes from 0 to 2 pi, right? Use that for your cut down table of values. Make sense? Okay. And that's it. We got about 3 minutes left. Yay. All right. Hopefully that made sense-ish.